So I'm going to talk about more interesting physical phenomena associated with interfaces. Okay, and then after that, I will talk about homomorphism between plane waves and transmission line problems, Brewster angle, surface plasmon, polariton, and so on. So let me begin with Brewster angle. And it probably is something that you have learned before in an undergraduate course, but you probably would learn about this from a different perspective in my course. Okay, so we have derived the Fresnel reflection coefficients, and we see that RTM is given by, say, beta 1z over epsilon 1 minus beta 2z epsilon 2 divided by the sum of the two, beta 1z over epsilon 1 plus beta 2z over epsilon 2. So this is RTM. And then RTE can be derived by duality principle, because we have learned that Maxwell's equations are dual to each other. So you can actually write down RTE by inspection. You just change epsilon to mu, and that would be your RTE. So this would be mu1, mu2 divided by beta 1z over mu1 plus beta 2z over mu2. So you notice a very marked difference between the two reflection coefficients. One of them is only dependent on epsilon 1 and epsilon 2. The other one is only dependent on mu1 and mu2. So that makes a big difference, because it turns out that in optics, at optical frequencies where you also can apply electromagnetic theory, okay, then mu1 is usually equal to mu2, meaning that there's almost no magnetic materials in the optical frequency, but epsilon 1 and epsilon 2 are not equal, and that is quite prevalent. So you will see that these two reflection coefficients, even though they look the same, they have quite different physics. And another mnemonics that I helped you with is that the TM reflection coefficients, you have epsilon 1 and epsilon 2, but for the TE one, you don't have epsilon 1 and epsilon 2, but you have mu1 and mu2. The reason being that if you have a TM wave, the TM wave is defined to be a wave where the magnetic field is parallel to the interface. So if you look at the electric field, then the electric field would have to be something like this. So at this interface, you can see that the electric field has a normal component, has a component that is normal to the interface between epsilon 1 and epsilon 2. This normal component of the electric field would have to imply that the flux of the normal flux has to be continuous. And you have this epsilon 1 and epsilon 2 appearing in your reflection coefficient. Whereas for the TE case, you have the electric field parallel to the interface. Let me put it this way so that the magnetic field can draw it like that. And the electric field is parallel to the interface, and hence it will not feel the presence of polarization charges at the interface. And hence, this reflection coefficient will not have epsilon 1 and epsilon 2 appearing in it, because no polarization charges are induced at the interface. It's just a good mnemonic, okay? So this makes a very interesting difference, which is that I could set the numerator of this to be 0. And you can find angles at which this is possible. Whereas when you set the numerator of this to be 0, when mu1 equals mu2, there is not too many angles, or maybe sometimes not at all, a single angle at which you can make this numerator going to 0, okay? Because, for instance, you can set epsilon 2 beta 1z equal to epsilon 1 beta 2z. Then the numerator of RTM would be 0. Okay. Whereas if mu1 equals mu2, this would only be possible if this one equals that one. And if you solve this equation, you can see that that is a contradiction. Okay, beta 1z and beta 2z are never going to be equal to each other if the two media are different. Okay, so it's not possible to get RTE to be 0, but it's quite possible to get RTM to be 0. And hence you can square this equation, since you know that beta 1z by the dispersion relationship in region 1 is beta 1 squared minus beta x squared. Okay, where this is the x-axis, and this is the z-axis. And then beta 2z equals beta 2 squared minus beta x squared. And beta x's are the same in both regions. 1 and 2 is because of the phase matching condition. So now I can square this equation. I can square that equation. I will get epsilon 2 squared beta 1z squared, because I want to get rid of the square root signs. So I will have this to be true on the left-hand side. And then on the right-hand side, I will also square it so that I will have beta 2 squared minus beta x squared after I have substituted in for beta 2z. Now I make this equation solvable by squaring it. And you can solve for beta x. Okay, you can solve for beta x. You can make use of the fact that beta 1 squared is omega squared mu 1 epsilon 1. Beta 2 squared is the wave number squared, and region 2 is omega squared mu 2 epsilon 2. And I will not solve it for you because this is high school algebra. You can actually solve it and show that beta x after you bring them to one side. And you can assume that mu1 equals mu2. Then if you were to solve that, then you show that the solution is given by this expression over here. Okay, you can do this at home if you want to. But this gives something quite interesting. Interesting in the sense that if I were to look into the physics of this in greater detail, I know that beta x is equal to beta 1 sine theta 1. It's also equal to beta 2 sine theta 2 because of phase matching. Beta x is the same in both regions. So this is beta 1, this is beta 2, and this is my x direction, and the x component of these two vectors have to be equal to each other. I have this relationship over here. So theta 1 is this angle in this region. Theta 2 is the angle in this region. Okay. So if you use this condition and use it in the previous equation over here, okay, you will find that, well, sine theta 1 is quite easy to show. Sine theta 1 is equal to square root of epsilon 2 over epsilon 1 plus epsilon 2. Okay, it's quite easy to show. You can maybe even see this from this equation. If I were to write this as omega square mu epsilon 1 sine theta 1. Okay, I can write beta x as this. You can see that sine theta 1 is the rest of the factor if I assume that mu is the same everywhere. Okay, so I get this factor right away. And then I get sine theta 2 to be epsilon 1 over epsilon 1 plus epsilon 2 by the same token, okay? This happens at Brewster angle. This happens at Brewster angle when the reflection coefficient goes to 0. That is what we did. We set the reflection coefficient to be 0 to get this equation, and finally arrive at the fact that at the angle at which the reflection coefficient is 0, the sine theta 1 and sine theta 2 have to be as such. Okay, and this makes it even more interesting because you can square the two equations. You can easily do this in your head. You take sine theta 1 square, and then you take sine theta 2 square. If I square this side and add it to this side, I see that epsilon and epsilon 2 are the same for the numerator. And finally, the right-hand side will add up to 1. Can you see that? Okay, square the right-hand side, add them up. Numerator and denominator are the same as each other. I get the right-hand side to be 1. Okay. Well, we also know another very interesting trigonometric identity that we learned in high school, that sine squared theta 1 plus cosine squared theta 1 also equals 1. Okay, everybody knows that from high school algebra. Probably these are known since Pythagoras' time. Okay, so now if you were to subtract these two equations, you will get the fact that sine theta 2 is equal to cosine squared theta 1. Or maybe I can just say that this sine squared theta 2 must be equal to cosine squared theta 1 if I were to either to eyeball them or to subtract them and arrive at this equation. Okay, so what does this mean? Well, cosine of theta 1 can also be written in the form that is more reflective of the similarity. This equation, I can say that sine theta 2 is equal to cosine theta 1. Okay, I take the square root to get there. I take the square root of the previous equation to get there, but taking the square root is a very dangerous proposition. I like to remind you of that. And I can write the left-hand side as cosine of pi over 2 minus theta 2 is equal to cosine of theta 1. Okay. So there are infinitely many solutions to this problem because I also neglect to put in the possibility of plus and minus sign when I took the square root. Okay, I'm just looking at the positive root solutions, and if you look at this particular case, you can see that theta 1 plus theta 2 must be equal to pi over 2. Is one possible solutions. Okay, there are infinitely many solutions, but we are only confined to solutions where theta 1 and theta 2 are less than 90 degrees because we're doing a real physical problem. So this solution satisfies the real physical situation that we are in. And so if we were to draw this picture, okay, the incident angle plus the transmitted angle at Brewster angle, these two angles sums up to 90 degrees. So pictorially, it will look something like this. At the Brewster angle, the incident angle plus the transmitted angle equals 90 degrees. And if you go through your high school algebra or geometry or trigonometry, then you know that this angle must be 90 degrees. Okay, this angle must be 90 degrees, and you wonder why. So at Brewster angle, the plane wave propagates in this region, but there's no plane wave being reflected. The plane wave entirely gets transmitted. Okay, there is a physical reason to explain this as well. The physical reason that physicists like to say, or the optics people like to say, is that if I have a dipole, the dipole radiates in a very special way. So what happens is that if you have an incident TM incident field, TM is the case where the electric field is like this. Okay, the magnetic field is like this. Okay, just to show you how the electric field is polarized and how the magnetic field is polarized. So as the wave propagates in the medium, okay, the H field is parallel to the interface or perpendicular to the paper, but the electric field is not parallel. It has a component that polarizes the interface. And what happens is that this electric field gives rise to little dipoles called the polarization dipoles. We know that P is epsilon naught chi E. Okay, whenever you have electric field, you have polarization density, which essentially consists of very small little dipoles. And these dipoles are special in the sense that you're going to do some homework on it, which is that if I have a dipole, electric dipole, then heuristically the electric field looks something like this. You probably have seen this in your high school algebra or high school physics. Okay. And then there's a current going back and forth in this dipole as it oscillates. And the magnetic field of this dipole, using Ampere's law, the magnetic field will look something like this. Okay, if I apply Ampere's law. So E field looks something like this, H field looks something like this. And you can do E cross H in your head. Okay, you can go through your mental gymnastic and do E cross H. And you find that E cross H is 0 here. If you were to look at the two ends of the thing, E cross H is always 0. Because at the two ends of this dipole, the electric field is completely radial. Okay, the magnetic field may not be radial. The magnetic field might still look like this. Okay, but it does not give rise to power flow in the axial direction, which we call the end-fire direction of the dipole. Hence, a dipole does not radiate in the axial direction. And if you use that physical understanding for this picture, these dipoles would not radiate in that direction. And these dipoles will only radiate in this direction. You will learn more about dipoles later on in the course. And that's why we don't have a reflected wave. At least that's how the optics people explain it. Okay, that's why we don't have the reflected wave, because we are at the end fire or the axial directions of all these dipoles. Okay? And what is more important is that because of the fact that the epsilon 1 not being equal to epsilon 2 for most material medium, so RTM can be 0. RTM can go to 0, but as you can convince yourself later, if you look at RTE, if you try to, well, set the numerator of this to be 0, you will find that this is not possible. It's not possible to make RTE to go to 0. You can convince yourself that this equation has no solution. Okay, this equation has no solution. And then if you were to look at the TE reflection coefficient, it does not go through a 0. But the TM reflection coefficient would go through a 0. And if you take the magnitude of the reflection coefficient and the magnitude of the TM reflection coefficient, this is always lower than the reflection coefficient of the TE polarization. This actually gives rise to something very interesting. It says that if you have a wave, say if you have sunlight, say if you have sunlight coming in at you, and then the sunlight is randomly polarized. So it gives rise to light. If you have a light impinging on the surface of the earth, that light is randomly polarized, is a mixture of TE and TM polarization coming in. Okay, so since it's randomly polarized, it will have both polarization in the light that is coming in to the Earth surface. But because the TM reflection coefficient is always smaller than the TE reflection coefficient, after being reflected, okay, then what happens is that the wave becomes predominantly TE, because the TM polarization has been mitigated by absorption by the surface of the Earth, which means that if you want to reduce road glare, say if you want to reduce road glare, say if you're driving in a car and you're in there and you would like to have some sunglasses that is of high quality, that it will cut out the road glare as well. It will not reduce the direct signal or direct sunlight from the sun, but it will reflect, it will reduce the reflected light from the surface of the Earth, and that is called road glare. And you will buy a pair of sunglasses that has that kind of property, where the TE polarization in this case is where the electric field is horizontal. Okay, so the electric field will be horizontal when it gets into your eyes. So you would like to buy sunglasses that will cut out this horizontal polarization of the electric field to reduce road glare. Okay, there's one application of this knowledge. And maybe some insects might use this for navigation as well, as you will learn later on. Maybe even birds. You realize that whatever being reflected has different polarization. Even the reflected light from the sky will have different polarization because of this preference for TE over TM and so on. So if you look at any surfaces, like glass surfaces, the reflected wave will be predominantly TE. And if you buy a good filter for your camera, you can actually cut out the glare of this picture over here, this window over here. And the picture you have taken is a lot of higher quality than what you have if you don't put in a filter in your lens.